Okay, we're finally going to talk about Stokes' theorem. And I like to think of this as just Green's theorem on curved surfaces. So you'll see what I mean. Let's just start by recalling Green's theorem. And that just says that if you take a double integral of this thing that we know as qx minus py, then we end up with f dot dr, provided that f is our usual pq, 2D vector. And the integral is over C, where C is the boundary of our region. So in an earlier video, I actually called this quantity here the two-dimensional curl of f. And so really what this thing is actually the z component of the 3D curl. Where, of course, now we're using a 3D version, where you just add a 0 to the zth component. So what is it, the zth component? It's just the kth projection of that vector. Right, if I take 0, 0, 1 and dot it with PQR, surely I'll get R. So really what this Green's theorem is saying, it's saying that the double integral of the curl of our 3D f dotted with k hat dA, this is going to be equal to f dot dr. And note that the 3D works just as good here, because our dr is 2D. And if you dot a 2D vector with a 3D vector, you get it's the same, because the last component doesn't contribute. So I'm just going to go ahead and call this ds. There's only one differential that we know that has a vector, so surely that has to be it. So now we end up with what actually is Stokes' theorem. And if we replace R with S, then I'm going to write down what Stokes' theorem is. And note that partial S, this just stands for the boundary of S. Okay, so this is actually Stokes' theorem. And I think it's worth noting why are we allowed to use ds here? That's because the normal vector of a planar region, it just points up. That's the unit. K hat is actually the unit normal vector of our surface, because our surface is planar. So we've shown that Green's theorem is a special case. Well, I wouldn't say, yeah, I think 2D is probably a fine way to say this. 2D or planar case of Stokes' theorem. Okay, and so what Stokes' theorem does is it allows you to use Green's theorem type techniques for curved surfaces. So for example, my favorite curved surface is the hemisphere. There's some other ones, like you can do cylinders. For example, you want you could do like one half full and the other half is empty. But on the other hand, you could do hollow cylinders as well. And so the S is just it's just a tube. And so how do you do Stokes theorem in that case? So here's what you do, you subtract. So I would use the full cylinder on one side, and I would subtract off this piece. So if you call this thing S1, you call this thing S2, you end up with the empty cylinder. And so your integrals, you'll just do subtractions. And so what it turns out is your curve, because we always use that positively oriented curve. So when we have this arrow going in the right direction, what happens is after we subtract, we end up having to use the opposite direction because there's that negative sign. So this part here, this will be positively oriented, and this part will be using negatively oriented. So these are for the line integrals. So that's the idea. If you have a domain with holes, what you do is you start off with domains without holes, and you do a subtraction to get your domain with a hole. Okay, in the next video, we'll talk about why Stokes' theorem actually works. Why are we allowed to do stuff like this? Thanks for watching.